to Lawrence Lootens, who's a postdoc, local postdoc here in Cambridge. Lawrence has done a lot of stuff about the physics of topological defects on the lattice, and he's going to teach us about that. Thank you, Lawrence.
Okay, thanks, Matt, for the intro, and thanks also to Ingo and Valentina for inviting me to talk a little bit about some of the research that we've been doing these past 10 years together with Frank Verstraeten, who's somewhere in the audience there. I titled these lectures Entanglement and Topological Defects on the lattice. The reason for this is that I kind of want to talk about a very concrete application of these ideas that you will hear about this week in many of the lectures about topological defects, interfaces, boundaries. It turns out that if you take a certain perspective on many-body physics, namely this sort of quantum information entanglement-based perspective that we have on many-body physics, it turns out that understanding all possible different boundary conditions, topological defects, interfaces, turns out to be very useful, not only mathematically to understand the structure of these kinds of objects that we are interested in, that I will talk about, but also to exploit these things in a computational way. So in some sense, these lectures that I'm going to give, I'm going to try and convince you that this sort of tensor networks, which is what I will talk about, sit at a very nice interface between both computational physics, mathematical physics, which I'm assuming most of you are more familiar with, and then quantum many-body physics, which are maybe more the QFT people. So that's kind of the motivation. Let's see, how do I do this best? I think we should start by doing this. So, entanglement. I will apologize for my handwriting once, and I'll not do it again. If anything's not readable, please just put it in. So, as I said, the motivation for these lectures is to try and understand and use the entanglement structures of quantum phase of matters, and we will be doing this using topological defects. So, the first thing I have to talk about a little bit, which is sort of point 0, is I have to tell you what is a phase. So when we say a phase of matter, what do we mean by that? So very concretely, let's assume that I give you some Hamiltonian H, with some parameters G1, G2. What you can do is make something called a phase diagram. Parameters G1, G2, and then you can draw these kinds of shapes, completely arbitrary. 1, 2, 3, 4. So this is called a phase diagram. It's telling you, as a function of these parameters G1 and G2, this Hamiltonian, or more precisely the ground state of this Hamiltonian, is in a certain phase. The example you may all know is something like the Ising model, where you have two phases, the symmetric and the symmetry broken phase. Or generally, it can be more complicated. It can be something more complicated. And a lot of the goal in quantum many-body physics is trying to understand exactly these kinds of phase diagrams. Whether you're interested in something like superconductivity, where you have some Hamiltonian with some parameters, and then maybe in one point of this parameter space you have a superconducting phase. That's interesting experimentally and for engineering problems. But also if you're interested in things like quantum error correction, there's a very strong connection between the physics of quantum phases and the physics of quantum error correction if you're trying to build a quantum computer. So these kinds of things have lots of applications. And so how do we define these kind of different phases here? How do we distinguish these? What does this line mean? Well, we say that 2 points are in the same phase. So, or let's maybe put it differently. 2 points are in a different phase if there exists no adiabatic path of Hamiltonians, of gapped Hamiltonians that interpolates between these two Hamiltonians. So let's say that I have a point here and a point here. If I try to take a path from this point to this point adiabatically, so slowly, and I try to do this in such a way that the gap of the system, which is the energy between the ground state and the first excited state, stays open, it doesn't close. If I try to do this along this path, I will find that necessarily at the point where it crosses this phase transition line here, the gap has to close. Right? That's what we call phase transition. So that's kind of how you can build up these phase diagrams, as basically 2 points are in the same phase if there exists such a gap path without having to close the gap. Now, that's sort of the normal definition in terms of the free energy and derivatives of the free energy becoming non-analytic. A more useful definition for our work purposes, which is completely equivalent, is sort of this quantum information definition, saying that if, let's say, let me call this point, I don't know, point A, point B, A and B in same phase, then this is true if and only if there exists a sublinear depth quantum circuit. That connects the bits A to B. So what do I mean by this? A quantum circuit is something that's most easily explained using this graphical language that you may have encountered before. So let's say that our system has some tensor product structure. Yes?
Write larger, please.
Yes, sorry. So let's say that our system has some tensor product structure, and let's assume that it's some one-dimensional thing, like this. A quantum circuit is something that you build out of local unitary transformations. So I'm imagining doing some kind of unitary transformation on these guys here. This is a local unitary transformation because it only has support on 2 sides, let's say. Right? So a sublinear depth circuit, what is the depth of a circuit? Let's say that I'm acting on these things more than one, unitary. So I do one layer like this, and I do another layer like that. This here would be a depth 2 quantum circuit. So if I have 2 points in this phase diagram where the ground states can be connected by such a circuit, it means they are in the same phase. Because this is not something that sort of can, we could prove that these are not kinds of things that can close the gap of the Hamiltonian. If
what did you mean by such a circuit?
a finite depth circuit, so like this, yes, sublinear depth. So in general, I'll have some, let's say I'm in 1D, I will have some linear length of the system, L. If the depth of this circuit grows slower than L, so even if it's something like logarithmic, that's still fine, then we say these 2 ground states are in the same phase. But if this is something that you can only do with something like a linear depth circuit or worse, then these things are in a different phase. So that's kind of operational definition of what it means to be in a phase. And this is something that will be useful in the kind of classification that we
There's a kind of understanding that these 2 ideas are equivalent.
Yes, exactly. So the way to prove this is using something called Lieb-Robinson bounds and quantum spin chains. That's a bit more complicated, and this is just background, so I don't want to go into this. But indeed, you can prove that these 2 ideas are exactly the same, which is kind of remarkable, but yeah, this can be shown.
Can we say anything if they're gapless, the phases?
Indeed, so this is the classification of gapped phases. Indeed, if they are gapless, so you're talking about not just these gapless points, but really like an extended region where, that was you're asking about, yeah, I'm not going to be talking about that. So this is just about gap phases and the phase transition between them. Okay. So I've talked a bit about phases, and as you already see, I sort of, rather than talking about Hamiltonians per se, it's equivalent to talk about the ground states of those Hamiltonians and talk about their properties if you want to talk about phases. So let's try and have a closer look at ground states of Hamiltonians. More particularly,
I have a question, Lawrence?
Yes?
Suppose you want to do a first order phase transition. So
Yes.
all the spins up goes all the spins down.
Yes.
Can that be implemented by a sublinear blah blah?
Well, that's just, it's a depth 1, right? If you flip all the spins from up to all the spins down, that's not a, you just do a local Pauli X. It's a local unitary transformation that takes all the down spins to all
In
the
your
up.
first picture, I would draw a line. I would say they were different phases. I undergo a phase transition.
Yes.
That doesn't close, but it's still.
But if it's something like first order, typically means that there's another path that means you can walk around it, right? Without having to do that. Okay, then maybe we're not thinking about the same thing. But something like first order doesn't fit in this. So this is about second order.
I think David wants to say that you want to have circuits that preserve symmetry.
Sorry? That respect the symmetry.
Yes, and it's more complicated.
Right, indeed. Okay, so these phase diagrams are only defined if you impose a certain symmetry. And so if it's something like 1 dimensions and you don't impose any symmetry, there's only one phase. If you say, okay, I have something like an isomol and I have a Z2 symmetry, you have to impose that symmetry on these circuits to get an interesting phase diagram.
I see. And then that a circuit with symmetry can't flip spin up.
Exactly, yeah, and then it's like a proper phase. Sorry, I should have, yes. Thanks. Okay. So ground states of local gapped. How do I do this? So, okay. Let's assume you have some generic state psi and some tensor product Hilbert space H A tensor H B. It means that, okay, there's some basis, i.e. psi, something like, so you pick a basis for this Hilbert space, you pick a basis for that Hilbert space, and then you can express this psi obviously in this basis, Ci, J, psi I, A, tensor J, B, like this. So generic state in this Hilbert space can be written like that. You can define something called the von Neumann entanglement entropy of this state as follows. So S given by minus the base of rho log A. By this rho A is called a reduced density matrix, and it's obtained by taking the trace over system B of this density matrix, which is nothing but sum over J of this C I J I J star I A I. So this is a measure, this entanglement entropy is a measure for the amount of quantum correlation between that this state has between system A and system B. So if this state is a product state, if it factorizes as some state on A tensor with some state on B, then this entanglement entropy is 0. And then the other extreme is where it's really just like an equal weight sort of, let's say that my psi is of this form, it's sum over I of I, A, I, B. This would be called a normalized square root of Z. This would be a maximally entangled state, so this would be something that maximizes this entanglement entropy. So this is just a measure for how much correlation is there between this one system and the other. It's saying, okay, if I know something about this state in A, how much can I tell about the state in A by just doing measurements in the state in B? How much are they correlated at the quantum? So it's really just like classical correlations, just the only thing that's special about this is that these kind of notions are basis independent. So in a generic quantum state, if I give you a random state psi, and let's now assume that I'm dealing not with just a bipartite state, but I have a multipartite state. So I have a state, I have a Hilbert space that's built up of many tensor product factors. Let me schematically draw this as something like this. So each of these dots here represents one of these tensor factors in my many partite Hilbert space. a generic state, the entanglement patterns, if you were to graphically try and draw them, there's a way to make this precise, but just for the sake of the argument. Generically, it would look something like this. Like everything would basically be connected with everything. Something like that. Okay. You can imagine what this looks like, right? And so if I were to now say compute the reduced density matrix of this tensor factor here, so I single out this guy, I compute the reduced density matrix, you would find that the entanglement entropy scales with the volume of the area that I've cut out. Right, that's a generic state. So if I give you a random state, this entanglement entropy here, the way it would depend on the size of the region that I'm sort of singling out would be volume law. Right? That's what happens for a generic state. So generic looks something like this. This is kind of the most complicated a state can get. Now, the other side of this is that there's something called area law. And that situation is very different. In that situation, your entanglement structure is more like this. Basically nearest neighbor kind of quantum correlations. So if you now cut out a region of this, let me add one more row, just so I can cut out two sides. If you now look at the reduced density matrix associated with these sides, and you check how does the entanglement entropy scale with this region, with the size of this region, because you have this area, it would scale with the boundary, with the size of the boundary of the system. So generic, you have this volume law behavior, and in this particular case, you have area law. And now the whole point of looking at this is that if you're looking at ground states of local gapped Hamiltonians, they satisfy an area law for the entanglement entropy. So this is something that you can rigorously prove in 1 dimensions. In 2 dimensions, it's something that everybody believes to be true, but there is no formal proof of it. And the same goes for higher dimensions.
So are you gonna define the property, the notion of locally gapped?
A local Hamiltonian, I mean it's built from, yes. By local, good. So let me do it here. So I mean that I have an H, which is the sum over I, J, where this I, J are some nearest neighbor interactions. So that's what I mean by local Hamiltonian. It's a Hamiltonian that's built out of a sum of local terms, where local means it's a sum of terms that only act on a few tensor product factors in my zone space.
I see.
And
So
then
local
gapped.
Hamiltonian is not locally gapped. Okay.
No,
you have a
sorry,
notion
it's
of-
local, comma, gapped. And then gap means, well, gapped. Okay, good. And so this is where tensor networks come in. So, let's see how I'm doing on time. So, tensor network. So, I told you that the generic state has this kind of area law, volume law entanglement, but that ground states of local gapped Hamiltonians have this area law entanglement. So if you think about sort of a cliche, and it's a picture that's drawn in every tensor network talk, but if you look at your big Hilbert space of quantum states, there's only a very tiny little corner. That's actually relevant if you're interested in describing the ground state and also actually the first few excited states of a local gapped Hamiltonian. So if you're only interested in the ground state physics of these kind of things, you don't want to parameterize your wave function in this way. You want to come up with some kind of parameterization that exploits this local entanglement structure efficiently. Because that would give you a huge compression in the amount of information that you need to describe this kind of state. So these states, they are called...
Can you just, what is this diagram?
This is a sketch for the space of all possible quantum states, so abstract thing.
Right.
And then there's a little tiny corner in here that's actually relevant for low energy series of local gapped Hamiltonians. And that little corner is characterized, is parameterized by tensor networks. Yes?
I'm still a bit confused what you mean by the area formats. Do you mean by the states near some point where C, IJ, CIJ star is large enough? Yes, when you calculate that? Or?
No, so I'm talking about this measured here, right? This is the entanglement entropy. I'm talking about the dependence of this quantity on the size of the subsystem A that I'm looking at. So here the subsystem, okay, I just took a single dot, which is maybe why you're confused, but imagine taking more than this, right? So if I compare this guy on one side versus this guy on two sides, I'm getting many more correlations. And if you look at the scaling of this, how this quantity depends on the number of sides I'm putting in here, you will find that it depends on the actual number of sides in here, right? Whereas if I do this here, you can kind of see that if I do it like this, and let's imagine that I have many more things in between here, for instance. Like that, right? Okay, I'm just kind of fine grading my image just to make a point here. So I've ruined my nice lattice, but you find that it only scales with the boundary because all the entanglement has to come from basically these connections that cross the boundary. There's nothing entangling this thing to something here in the bulk of this thing, right? So it only scales with the perimeter of this thing. That's what it means to be an area. That clear?
Sorry, could I?
Yeah.
So in your notion of a local Hamiltonian, right?
Yes.
So you fixed a graph somewhere, I guess, right?
Yeah, sorry, indeed. So I'm assuming I'm working in some dimension where, okay, you could say dimension, what does that mean? I have some tensor-product Hilbert space. The dimension is basically inherited from the Hamiltonian, right? If I say I have a Hamiltonian in 1D, that means that I have some tensor-product Hilbert space, and then the locality of these interactions determines the dimension that I'm working in.
Right, but I have to have fixed a graph
Yes.
structure somewhere in order to talk about something local or
Yes,
not. Right?
exactly.
Yeah,
Yes.
I was just a bit confused because your two pictures are different, but even with the same graph, some Hamiltonians are local and some are not. Right?
Exactly. Yeah, indeed. So you could say, well, in some sense, it's kind of defining what it means to be local. You could say, well, okay, if there's very long-range interactions, should we even call this a two-dimensional Hamiltonian, right? What does it mean? Because everything's connected to everything.
And in this discussion of the entanglement entropy, you're always taking the vacuum state of the system and then writing it with respect to two subsystems.
Yes. Yeah, exactly. So I'm talking about the ground state of this thing, right? Of course, the eigenstates of this Hamiltonian form a full basis for the whole Hilbert space, right? So, yes. This is about low energy physics, which, okay, is relevant for many systems that we actually care about. Okay, so the simplest kind of example of tensor network state is matrix product state. So in 1 + 1 dimensions, I will be writing 1 + 1. So I mean one space dimension, one time dimension by this. There's an ansatz called matrix product state, and explicitly it looks like this. Given by this expression, so it's a trace over I1, 2, I, and 1. So this is some basis for my tensor product Hilbert space. And I'm saying the coefficient, the Cij here, I'm expressing it in a very particular way. I'm expressing it as a product of matrices. So these AI, they are D by D matrices, where D is called the bond dimension of this matrix product state. So a few things are important. This state is clearly translation invariant. So already that's something that's not so obvious to do. If you write down a generic state like that, it's kind of hard to impose that it has to be translation invariant. If you write it like this, it's translation invariant by definition, because I can sort of, I can permute these things and it doesn't change anything to this prefactor here. Another thing is that this is a state in a Hilbert space. So this is a state in, let's say, C, this number here is in C little d n. But it's only specified by this d by d matrix, right? So this is something that's exponentially big. The number of coefficients you can put here is something that's exponentially big in the system size. But with this parameterization, you only have d squared parameters, right? So this is a massive compression of this possible Hilbert space of quantum states. There's only d by d parameters that define this whole state. So graphically, because we tend to use the graphical language for these tensors, we would write this state as follows.
Sorry, Lawrence.
Yes.
Small t is the physical dimension. We have the small t.
Little d is the physical dimension. So indeed, I forgot this. I1. There's a sum here. Little d. 1. So these local Hilbert space are little d dimensional, and then the big, sort of these virtual Hilbert spaces, they are capital D dimensional. Should maybe use chi instead. Let's use chi. That's a bit more conventional. And then I won't confuse everyone by using two different words. Okay, so graphically, if you write
I
that,
can't read that summation sign. You're summing over the i's.
I'm summing over the little i's, yes. And then for every configuration of little i's, there is a matrix here. So this matrix depends on this little I. Fixing these i's fixes me a set of matrices, and then the coefficient is obtained by multiplying entries. Right. Right, so a generic state, let me write down a generic state psi in this Hilbert space, so in this Hilbert space, which is C, E, tensor n, it looks something like this, right? It would be the sum of these I1, I2, times some coefficients CI1, CI2, IN, times I1, I2, IN, right? This number here is a complex number with d to the n parameters, right? Which is exponential in n, obviously. So as I grow my system size, I need to specify more and more of these numbers. It's not something that is feasible if you're trying to do computations. It's not something that you can actually work with. For system sizes that are modest, like if this is a two-side on-site dimensional Hilbert space, 40 sites is about as big as you can put on a computer, and then you're done, right? Whereas this, independent of the system size, only depends on chi-squared complex numbers. Well, sorry, there's d of these matrices, so I have d times chi-squared complex numbers that determine the state completely. Right, so it's something that's independent of the system size. It generates a state in that Hilbert space.
N times.
Sorry?
N times chi square, right? Your notation.
D. So these little I here, they are the, so I have one matrix, right? This matrix is the same everywhere. Right? That's the whole point. It doesn't depend on n. It's just the same matrix repeated over and over again. And I can create a state on a billion size with this amount of parameters. Of course, this is a massive compression of the Hilbert space, right? A generic state, I won't be able to write it like this in an efficient way. But the whole point will be that these states are exactly these states that satisfy an area law, and that these states are the states that we are interested in the low energy physics of a local gapped Hamiltonian. So yes, it's a massive compression, but we are lucky that nature is the way it is, that this compression is actually useful. It's a useful class of states. It's the space of states, of ground states of local gapped Hamiltonian.
Sorry, just to make sure.
Yeah.
So you fixed some matrices here in this manner, and
Yeah.
you construct. So this is the definition of your states IA. Is that
Yeah. So this is called I should write the name, matrix product state. The name is sort of obvious.
Chi, that is from what?
Chi is the size of these matrices.
So does it vary?
It doesn't vary, it's constant.
No, I mean which values can be assumed?
Oh, whichever you want. You choose something, so you choose some A here, which means I choose some set of chi by chi matrices, where chi is something you choose. The bigger you choose chi, the more entanglement you can put into that state. So we will see in like 2 sentences, I'm going to say something about the entanglement entropy in this kind of state. And then we will see the dependence on chi. So let me maybe jump to that, and then if you're still
So this shaded in corner that you've drawn on that abstract diagram, so this is the space of ground states of gap local Hamiltonians.
Yes. Yes. So the point is that, okay, this chi, if I take chi big enough for a finite system, I can express any state. The point is going to be that the way in which the space grows, so actually, okay, let's say that I draw this corner explicitly as a function of chi, the space of states that I can span for a given fixed chi, this space will grow, of course, right? And if I take chi big enough for a finite system, at some point I will be able to represent any state. But the point is that, okay, as we are moving out here, we are increasing the amount of entanglement, and you don't need chi to be that big. So taking chi to be some finite value is a good approximation, or in some cases gives you exact ground states for these local gapped Hamiltonian.
I'm sorry, this state by itself has nothing to do with the Hamiltonian, right?
No, no, indeed, I define the generic state here, right? I'm not talking about a particular Hamiltonian. Now, you can always, for any matrix product state, okay, let me first draw it graphically, but for any matrix product state, you can find a local gapped parent Hamiltonian that's frustration-free, for which this is the ground state. So you can convert statements about these matrix product states to statements about this Hamiltonian by doing this parent Hamiltonian construction.
So there's some Hamiltonian fitted to this state.
Exactly. Okay, so,
One quick question. What's the counting of the number of translationally invariant states in the probability space? How does that scale with F?
You mean generic states? I'm not sure how to generically impose translation invariance on. You're talking about this state, right? Okay, I suppose it's just I need this thing to be invariant under translations, right? So I guess it's just this divided by n, right? I have n. I have this thing which is generic, but now you're giving me n constraints on this thing.
Still goes exponentially with it.
It's still exponential. Yeah, for sure.
I'm sorry to keep asking questions.
Yeah, sure,
but
that's
the
fine.
part that came up. What is translation?
Oh, translation means shifting all these sites over by one. So saying I1 goes to I2, I2 goes to I3, In goes to I1. So I'm imagining I'm on a ring, and I'm looking at this state here on a ring, and I'm asking, okay, if I now shift all my tensor product factors over by one side, what state do I get? So I basically just replace this.
I guess I understand, but I thought all these things were living on some graph,
Yes.
right? So when you're doing, and then this is just some arbitrarily.
Yeah, so
numbering
now
sites as
my
a
graph is not arbitrary anymore, right? I'm assuming I have a one-dimensional line.
Oh, it is a line now.
Yeah, now it's a line indeed. Sorry. Yeah, it's a line. And okay, you could think of this as living in some other space, but the entanglement structure of this is very much line-like, right? This thing is entangled with this thing, which is neighbor. But okay, I'm going to draw this thing graphically, and it's going to be very clear that there's some intrinsic graph underlying this. So graphically, we just draw this like this. It's very easy. Okay, because I'm taking a trace. I have to do like that. So this is I1, I2, In. So this is graphical language that we use for tensor networks. It's quite simple. It's really a tensor is represented by something with a number of legs. So this is a rank. For every value of this I, this is a matrix, but another way of saying is that this is just a rank 3 tensor, right? Where I have dimension chi, and dimension d. So I draw this as something with 3 lines, and then a contraction is just a connection between 2 lines, right? So this picture and this picture, they convey the same information. And I should write times I1, I2. because this is just a number. These are just matrices or tensors that you like that you contract times this vector, which is this. So here you see that there's some intrinsic one-dimensional structure into this thing.
Does this state automatically satisfy the error law?
Yes, yes. So if you look at the entanglement entropy of any subregion of rho, well, let me, subregion, I don't know. I used A before, I don't know, subregion B, rho B of this state, you will find that this has to be, it's upper bounded by the log of chi. So the most amount of entanglement you can have between the subregion here and its neighbors is log chi. That's basically, okay, you have this matrix here. The way to compute it from this is, okay, I'm not going to go.
It is independent of the internal space D, small d.
Yes, it's independent of that. Yeah. So, of course, the internal space D determines the amount of linearly independent states you can write down in the space, but it doesn't change how much entanglement there can be with respect to this kind. The way to see it is that graphically, very quickly, if you try to compute this reduced density matrix, what you would do is something like this. You take the overlap, so this is a bar. You trace out some of these things like that. This would be like, okay, I'm on 3 sides here, and I'm computing the reduced density matrix of this guy with respect to this. So I've traced out this one and this one. And you can see that basically the rank of this matrix, so this thing was replaced by something, basically by, like this, like rho, like that. So you just contract all these things, you're left with this thing. Now the rank of this matrix is bounded by the bond dimension that you can get here. So if you kind of are looking at this as a matrix from this leg to this leg, you find that all the information has to go through these virtual legs here. And that's why you get this bound. I can work this out in more detail. I didn't want to go into this, but if anyone cares, I'm happy to do it later.
I think you're missing a factor of 2.
Because I'm cutting. Yeah. Okay. So the final thing I want to say about these, well, okay. So the definition of these tensor states is that there's an obvious generalization of this to higher dimensions, where I just take tensors of higher rank. So it's basically, I'm doing the same kind of construction, but I define them on a bigger Hilbert space. So this is now a 2D version of this picture, where, okay, I'm doing some kind of boundary conditions here. And this is the same thing as before. If you look at the entanglement entropy of this kind of thing, you again get an area law, almost by definition, because kind of the way the entanglement is routed in these kind of states is only through these virtual bond dimensions. So this is now just a rank 5 tensors. I have 4 of these virtual legs and 1 of these physical legs, and this just defines a state in 2 dimensions. For historic reasons, this is called a projected entangled pair state, or PEPs for short. You may think that something like tensor product state or something like that would have been a better name, but if you have complaints about this, you can take them up with Frank, who came up with this name. That's not I'm not responsible for this. Okay, so talked a bit about these tensor network states and hopefully convince you that they are useful. something I should say about these things, which is actually why 99% of the community in tensor networks is working on, is that these states form the basis of a variational algorithm. So you can devise a variational algorithm over the class of matrix public states. It's called the density matrix normalization group, or DMRG. And it works amazingly well. So it's kind of the state of the art for computing ground states of local gapped Hamiltonians. So there's a very efficient algorithm for a given Hamiltonian, a given local gapped Hamiltonian, to find a matrix Prolix state that represents or approximates its ground state. And it's something that's extremely efficient. You would think that finding the ground state of an Ising model on 200 sites is completely impossible, but using these kind of things, this just runs in 10 seconds or something like that, right? So it's kind of, this algorithm has been kind of a revolution, and it's really now enabled us to kind of break down this exponential wall for simulating many-body field, for simulating quantum many-body problems. So that's in 1D. and 2D, similar algorithm exists, although there the situation is a bit more complicated and people are still researching on how to best kind of approximate these things. But these things live in a kind of, although I will be using them as theoretical tools, these things live in a much bigger context of trying to simulate and understand quantum many-body problems. And that's what most of the research on tensor networks is going to. And the kind of goal of these lectures is that I will try to convince you that understanding the symmetries of these kind of things in terms of topological defects and boundaries is something that helps us improve these computational methods. Yes?
The dash represents matrix product, and double dash represents traces.
Oh, did I write a double dash? No. No, sorry.
They're all just products.
All just contractions. Yeah, these are just normal contractions. I could write this out in the same.
You have this kind of 3D line going into the board, and that's what.
This is an uncontracted edge here, and this is something that if I
This is non-contracted.
Yeah, this is uncontracted. It's like this here, and so it's something that's basically contracted with these guys, if you like, with the basis vectors of them. Because this is just a number. So these are basically.
It's not a 3D picture, no.
No, well, this is sticking out of the board, right? So
but it doesn't go further in. So
no.
It's just to represent those.
It's
loose
indeed on a plane, and then these are sticking out like that. Indeed. But you can then go to even higher dimensions, and then, of course, right? Or construct these things on more complicated lattices. Look at hyperbolic lattices, which is something that's relevant if you're looking at critical systems, things like that.
So are your lectures going to focus only on the 1+1D case, or will you also?
So I will talk about the 2+1D case, sort of the nice, exact topological 2+1D case, which is going to be related to states and constructions and topological quantum field theory. But then I'm going to use those nice topological 2D PEPs to say something about generic 1+1D states that are not at the fixed point and things like that. So that's going to be the kind of the goal. This kind of holographic reduction. It's useful to think about things in 1+1D as living on the boundary of something topological 1 dimension higher. That's the goal.
Sorry.
Yeah, sure.
Again, really stupid question.
No, that's fine.
I should warn you, by the way, I'm a stupid mathematician.
That's okay. I'm a stupid engineer. So.
But the thing is, so you were talking about using these things to approximate the ground states of various Hamiltonians of various systems, right?
Yes.
So these graphs you're drawing in order to produce the states of interest, approximating states of interest, the graphs are related to the physical structure of your system?
Yeah, so they are sort of inherited from the Hamiltonian, right? So if I give you a Hamiltonian and I give you some interactions,
right.
You want to choose the graph of the states to match the interactions in the Hamiltonian.
But it doesn't necessarily have to do with the physical structure of your system, or does it?
Well, typically we say, okay, I have a Ising model in 2+1 dimensions, which something I have spins sitting on a square lattice with nearest neighbor interactions.
Oh, I see. The Hamiltonian will already incorporate.
Exactly, the Hamiltonian, the locality of the Hamiltonian. Because I'm talking about local gaps, this locality requirement here imposes some kind of graph structure on the line.
Do we have any knowledge that if there exists any state which satisfies the error law but which is not the matrix product state?
In 1D, I don't think so. I have to ask Frank, but are there states, area law entangled states in 1D that are not represented as a matrix product states?
It depends on how you define the area law. If the area law is defined with the von Neumann entropy, yes. If it's
Indeed.
with the Range entropy, no.
Yeah.
But the Range entropy with alpha smaller than 1.
Yeah.
For Neumann entropy,
But
the answer is yes.
You're saying that for von Neumann, then any area law entangled state with a von Neumann area law entanglement is a matrix product state.
No, it's not guaranteed. You can
Oh, sorry,
find
okay,
construct
converse.
examples.
Yeah, I see. So you have to have all Renyi entropies for it to be a matrix product state.
Well, just one Range entropy is smaller than 1 is enough.
Okay.
Because Range entropies, when they are smaller than 1, are more sensitive to the tails.
Yeah, I see.
So that's what you need.
Yeah.
Sorry, can you summarize what's the conclusion?
Yeah, so there's different kind of entanglement entropies that you can find. So this is von Neumann entropy, is just one entanglement measure. There's other entanglement measures, the Renyi entropies. If you have an area law with respect to all of those different entanglement measures, then it's a matrix product state. But there are, if you just say this guy, then Frank is saying that there are counterexamples to this. And it's because this is kind of insensitive to the tails of your distribution. Whereas your Renyi entropy is something that picks up the tails of this kind of entanglement distribution more. And that's something that you need to have. Okay.
Is it possible to phrase the area law without referring to the model at hand? So
You need,
bottom left corner, the chi appears.
so you mean without reference to a Hamiltonian? Because I need a state, I need to be able to define entanglement, right? For which I need a notion of tensor product structure in my Hilbert space. I need my Hilbert space to be basically a tensor product of local factors to be able to define one, entanglement entropy, and two, define a notion of taking different subregions within that. That's all that you need to define an entanglement entropy and a notion of dependence on the size of the system that you have. If you have that, then you can define area law.
Should we write it down?
I mean, okay, I really just need, the only thing I need is that I have some psi, that's an element in H1 tensor, H2 tensor, H3, and so on, right, Hn. And then you could say an area law is something where I take my rho as a trace over some subset, I don't know, of the I don't know how to write this properly, some subset A of this thing, psi, like that, where this A is some subset of these indices here. And then you could look at how the entanglement entropy of rho A depends on the size of A, something like that. It would be like a general kind of definition of entanglement entropy, and the way it depends on the size of this thing. And then,
Should be linear size.
well, for that, you also need extra structure to be able to say this is volume versus area, right? So let's say that we are now imposing that there's some linear structure here, that there's not just some arbitrary graph, but there's some linear structure here. If this were area law entanglement, then this basically has to be bounded by some constant, right? Because the perimeter of an interval is some constant. It doesn't scale with the size of the interval, right? The boundary. But if this scales with the size of this thing, with the size of the interval that I'm cutting out, then we would say this thing is volume law entanglement.
It should be bounded by a number that is independent of the size of A.
Yes, that's an area law. And then there's something in between where this depends logarithmically only, so very, very weakly on this size, and that's what you get in a critical system. In a critical system, you have area laws, well, not area laws, you have entanglement entropies that depend logarithmically on the size of the system that you're cutting out.
I suppose even abstractly, you could say this depends on the size of A to some power, and if that power is less than 1, that's sort of like...
Yeah, that's fair indeed. Yeah. Okay. All right. kind of going slow. I don't know, maybe for some people that know these things. Hope I will be saying something for everyone. Okay, so let me kind of revisit this idea of phases of matter now, armed with these new fancy tensor network technology. So, phases of matter. Matter. Again. So it turns out that basically using this idea of this correspondence that we already hinted at, that matrix product states and Hamiltonians, there's sort of a one-to-one correspondence between local gapped Hamiltonians and matrix product states, but also vice versa. For any matrix product state, I can define a parent Hamiltonian for which it is the ground state. So I sort of have a dictionary between these two things. So when I'm talking about classification of phases, it's kind of the same as talking about classification of matrix product states and how they transform under symmetry. So that's what we will look at now. So,
Sorry, what's your other one there? I couldn't tell.
phases of matter again.
Okay.
Sorry. Yeah. So let's have a look. Okay, I need one thing in this whole tensor network business. There's like one thing that we call a theorem, which for mathematicians is probably not really a theorem, but we use it so much that we call it a theorem. So much so even that we call it a fundamental theorem. So let me write this out just once. Fundamental theorem of matrix product states. And basically says that if I have a matrix product state generated by some tensor A, so this is just, I'm doing this construction, I'm plugging in some A. And I have this equality for any system size. So I have two tensors A and B that generate the same matrix product state for any system size. Then this can only be true, so this is if and only if A related to B by a similarity transformation. So one direction here is completely trivial, right? If I take this state A here and I do a similarity transformation to these matrices A, it will generate the same state, right? All these x's are going to drop out in the trace, so that's completely trivial. The part that's less trivial is the converse, that if this is true for any system size, then this holds. That's a bit less trivial. I'm not going to prove it here. There's a few different ways of proving it. The traditional way is proved using Cauchy-Schwarz. I'm not going to prove it here. I'm happy to talk about it if you want to know more. So this is kind of the workhorse of a lot of theoretical results in tensor networks. And what it's allowed to sorry? Yes?
You need to put in that A and B have the same size, right?
Yes.
Otherwise you can just pad it out with zeros, right?
Yeah, but I'm thinking that even if they are not the same size, I'm thinking that then you just take these to be rectangular matrices where you take up pseudo inverse and then it's probably still fine. But okay, let's say that A and B are both chi by chi matrices. I'm pretty sure it's fine if you don't take them to be the same size, because then it'll just mean, okay, if they are the same state, it will mean that one of them is just too big. Okay. And then you can just get rid of these things for free, right? So.
But you're assuming that you're injecting.
Yes.
Expand the full matrix algebra.
Oh, sorry. Yeah, indeed. So yes, so they have to be the same size. Yeah. So I'm assuming that the matrix algebras generated by this set of matrices here is the full matrix algebra. And therefore, okay, if these matrix algebras, it's basically saying if two sets of matrices generate the same matrix algebra, they are related by similarity transformation. That's another way of saying this theorem. But indeed, there's a condition there that these tensors are sort of irreducible. There's no stupid zeros, or it's not like the direct sum of two other things. Indeed, that's an assumption. I didn't want to get into it.
Is it the same matrix X for each index I?
Yes.
Just one matrix.
Yeah, so I'm assuming here that is for translation invariant. There's a version of this where it's non-translation invariant, and then this X will depend on the system size. on the specific site.
We don't care about the fact that with regard to states and the same state, if they differ by a phase.
Yes, so indeed, so technically, indeed, you're right. I was hoping that there would be so e to the I. There's a phase there, indeed. Yeah, of course. Because it doesn't make sense to compare states just on the nose, right? It always has to be some e to the I phi, and then this has to be e to the I phi divided by n, basically. And then it works out again.
Phi now can depend on I?
This one, no, it's still independent of I. It's just an overall, I mean, when I'm comparing this, as correctly pointed out, it doesn't really make sense, right? I have to do this up to a phase. Because these things are raised, right? And so the only thing I can prove from this is that there's something where there's also phase here. And actually, if you compare these two things, you will get this to the power.
I'm sorry, from a physics point of view, of course, you're looking at rays.
Yeah.
You could literally write down that equality as vector.
Yeah, of course, you can impose this.
They don't need a phase.
Yeah. I'm just saying that there's cases where, okay, even if you don't put anything here, there could be a thing here. Such a way that it drops out when you actually contract it. But you can also put a phase here and that will show up here as well. Yeah, of course. Yeah. This actually becomes relevant in the classification of translation invariant phases. But this is not something that's... Okay, well, there's an invariant associated to this phase, but it's not stable under changing the number of sites. So it's only there if you impose translation invariance. If you don't do that, then if you allow yourself to block things together, then this kind of thing disappears. Okay. So something that's very nice, and actually historically one of the kind of the way that certain kinds of topological phase was first understood is the following argument that I will do now. So we have this kind of statement. Let's now assume that I have a matrix product state that's invariant under symmetry. So I have some U of G, which is some small U of G tensor N. So this is some on-site symmetry action, so G is an element of a group. This is some on-site representation of a group. This is a matrix, it satisfies the group multiplication rule. It's a unitary matrix. And let's consider the following. I have U of G tensor N acting on a matrix product state, psi of A N. And let's assume that this state is invariant. So this state is symmetric with respect to this on-site group symmetry for all G. And of course for all N too. Then I can use this theorem here. So maybe before I use it explicitly, let me write this down graphically because it's a bit easier. So this just means that x minus 1 a x is equal to b, like this. Graphically, that's what it means. So now I have a situation here where I'm comparing a state generated by the following MPS. I have a u of g, and I'm saying that this state and this MPS here, they generate the same state. So I know that by my theorem that these have to be related by x minus 1 x g, right? So I'm just applying this theorem here to this thing. So this is saying that if I have a matrix product state that's invariant under the on-site action of the symmetry group, it must be related to the original state via this invertible transformation on virtual degrees of freedom. Now, if you do this twice, what you will find is that this x of g, g1 times x of g2, they have to form a representation of the group, xg1, xg2, but only up to a phase, so only up to the I, what did I use here, phi that depends on g1 and g2. So in other words, this is a projective representation. So this x of g here is a projective representation. U of g here is just a linear representation. X of g is a projective representation where this phi here is an element of h2 of g versus U1. So it's a 2 co-cycle, it's an element of the second cohomology of G versus U1. And now, what I'm not going to prove, but what you can prove, is that this phi here, so this is some group, right? The second cohomology is some group. So for any given matrix product state, I will have these projective representation, and I will be able to extract some phi, right? The point is that this phi is not something that you can change with a linear depth G-symmetric circuit. So this phi here is an invariant of this phase, right? If we impose the symmetry G to our quantum circuits that we are allowing, that we are using to define what it even means to be in a given phase, we find that this phi here, this 2 co-cycle, is not something that you can change with a finite depth G-symmetric circuit. If you allow yourself to break the symmetry, then because of what I said before, that there is no phases in 1D, if you don't impose a symmetry, then you can change its phi. But if you impose the symmetry to the circuit, if you protect this circuit against perturbations or whatever, that will break the symmetry, then this defines topological phase. So these are called symmetry protected topological phases. And this is kind of exactly this argument is how they were first properly understood in lattice models. There's some very early examples of matrix product states from the 80s by Affleck, Kennedy, Lieb, Tasaki, the ATLT state, which was understood as kind of a different phase than was understood to be in the Haldane phase, which was known to be an SPT phase. But this kind of gives you a general way of understanding these kind of things. And it uses this fundamental theorem of matrix product states. Yes?
So, to be clear, when you have this UG on the side, is it conjugating all of the A's by some XG? Is that the same?
Yeah, that's what this is saying. So.
And then how do you use the fundamental theorem to...
No, sorry. I'm using this to say that this is the same.
I see, so...
So I'm starting from this. I'm assuming the state is invariant under this, right? So what this means is that this thing and this thing without the axis, they generate the same state. Then I employ this theorem. So B here in this case is basically, B is A times UG, and A is just A, right? Then I employ this theorem to say, because these generate the same state, it must mean that this is related via this virtual transformation. And then I derive properties of this virtual transformation. And okay, then I'm not telling you, but you can prove that this is something that's stable under.
So you have a co-cycle for this X inverse X, basically.
Yeah, so indeed, that's the point, right? This is just a linear action here, so there's no room for this to be projected. That would change the nature of this thing. But because there's an X minus 1X here, of course you're right, this thing here would drop out because you're conjugating by it, right? So there's freedom to put this number there. Exactly, that's a good point, thank you. Yes?
So is little UG a D by D matrix?
It's a little d by a little d matrix, yes. Yeah.
Sorry, so I guess here you said something earlier about these A's and B's generating the full matrix algebra, something like that.
Yes.
I guess you're using that here.
Yeah, so this is something that you use when you're proving this theorem.
Oh, that theorem.
So I'm assuming here that this is called an injective case. Yes.
And then when you use this terminology like symmetry protected topological phases, I guess I should look at these psi A's as being the ground state of
exactly. Exactly. So I'm sort of translating the discussion of Hamiltonians to the discussion of ground states because of how I have this dictionary. So I can now, for any of these states, construct a parent Hamiltonian, which will be the symmetry protected topological phase.
Right, but then you expressed this this phase in terms of this unitary transformation that bound under types of unitary transformations. But then if I want to think of these as parametrized Hamiltonians, are A's the parameters? What are the parameters?
Well, indeed, so you can perturb these states, so you can deform these by acting with constant depth quantum circuits, which will leave them in the same phase, and then your Hamiltonians will just be, okay, you conjugate with those constant depth circuits. Or, well, you can do more than just unitary transformations.
So the parameters of the Hamiltonians in terms of which we're speaking about the phases are some these unitary transformations themselves. Is that what you're saying?
Right, but you could also just say, okay, these constant depth unitaries acting on this MPS will define a new MPS, so you can just directly parameterize the parent Hamiltonian. So I mean, it's literally, this parent Hamiltonian is a function of these.
Okay, yeah, no, that's what
you're asking. There was a question there as well.
This type of state, symmetry transformation brings out.
So you're saying, can I put a phase here? So even if you don't put a phase here, which is the same as before, there can still be a phase here. So I was a bit cheeky and I sort of omitted this because it's a bit annoying. You can put a phase here, and then this will get you a richer classification. So there will be a phase here that you can prove has to be a 1 cocycle, which is nothing other than just an abelian representation of the group. A one-dimensional representation of the group. That 1 cocycle is also an invariant if you don't allow yourself to block system sizes together. So if you don't allow transformations between systems of one size to systems of another size, then this is an invariant. You cannot change this one-dimensional representation. And that sort of enriches this classification. However, if you allow yourself to block size together, that phase is not invariant anymore. It can change. So basically these phases, they start multiplying with each other, and it's no longer invariant. Now you can also assume that this is only true up to phase factor here, which, okay, if it depends on the system size, then you can just absorb it into this thing. If not, then I suppose indeed you can just go through the same argument and you'll just get an extra factor here and everything. So, yeah, David.
The group G could be discrete or continuous. It could be a Lie group.
Yes. So for sure discrete, then this is all solid. For Lie groups, I'm thinking yes. Yeah, I think it's the same for Lie group. It doesn't really matter.
I suppose it's SUN.
Yes. Okay.
Then is this cohomology trivial? I'm just trying to.
I'm not sure. I don't know enough about cohomology of. I think so. Yeah. For SU2 it's trivial, right? So for SO3 it's C2. And then if you look at the double cover, it's just SU2, right? And then I'm assuming that the need for SUN is the same.
U1, this cohomology is Z?
No, I think it's trivial also. It's the third cohomology of U1 that's Z. I think the second is trivial.
This isn't the anomaly.
This is not the anomaly yet, no. The anomaly is one higher thing than this. That's the next thing I'm going to talk about. Well, maybe.
What's the continuum field theory analog?
This is about edge modes. So this is telling you that you have edge modes in your system that transform projectively. That's the kind of continuum story. Yes, sorry, there was another question there, I think.
I think you answered it. What is the observable of this property?
How do you see this?
Yeah, if I want to measure something.
Right. So just like you have normal order parameters for symmetry and symmetry breaking phases, you have something called string order parameters for these kind of phases. So in these phases, you will find that the local observables, they will look the same. So you cannot distinguish between them just using, you cannot distinguish an SPT phase from a non-SPT phase. Just using local observables, but if you're looking at string order operators, then you will see a difference there. So that's the observable. And of course, in context of quantum computation, these SPT phases, they have a kind of interesting entanglement structure that makes them useful as resources for something like measurement-based quantum computation and all these kind of things. So these SPT states have interesting entanglement structure that is useful for these kind of things. Yes?
So I don't know if you said, but in defining an SPT phase, we specify the ground state terms?
I'm assuming that there's a unique ground state there, because I'm assuming that these MPSs are injective, which means that if there is a generalization of this where you have symmetry breaking, and then you can have partial symmetry breaking where the non-broken subgroup can be implemented projectively. So there's a nice interplay of all these kind of things, and that's completely understood. And I will talk about this maybe in a later lecture, but yeah, that's completely understood.
Sorry.
Yes.
Probably two questions. The one is, is the solution of that equation for A unique, or?
Yeah, so if given an A that satisfies this property, this xg is, if I do it like this, it's just a linear problem, right? So this is a linear equation for x of g. So given A and UG, this is a linear problem for xg.
So, but is A unique?
You mean?
I mean, satisfying that, any A will give a major product state.
Yeah.
To satisfy this condition, you need to satisfy this condition. So A is not arbitrary, right?
No. So the point is here, I'm trying to classify, given a generic matrix product state built from this A, and given that it is invariant under this symmetry, right? What is sort of a classification of these A's? Yeah. And I'm saying that these A's are classified, whereby classified I mean up to constant depth circuits and things like that. I'm saying that, okay, there's some property here that you cannot change under these constant depth circuits. And that's the classification of these A's, or that's the classification of in which inequivalent ways can this A transform under the symmetry. That's what I'm classifying. Now, of course, I mean, I don't know if you're asking about this, right? Of course, this A for a given state is not even unique, right? I can just conjugate it by any invertible matrix, but that would just be the change of basis for this projective representation. That wouldn't do it.
Well, and also, two major product state can be different, but they might represent the same phase. Right?
Yeah, exactly. But then the thinking is that they are. Yeah, sure. That both of those states would satisfy this property, right? So the point is indeed that if I have two matrix product states where the virtual degrees of freedom transform according to the same class of projective representations, there will be a finite depth G-symmetric circuit that connects them. That's the whole.
Okay,
that's the definition of what it means for them to be in the same phase. But it's not just a definition; it's something that matches this older intuitions about adiabatic gapped paths.
Yeah, that finite circuit applied to all state.
Yeah.
Right? But for major product state, you have a more refined.
You mean you have
expression?
Yeah. So if you have two matrix product states that are in the same phase, you can explicitly construct that circuit from those two that interpolates basically between those two states in such a way that the gap of the parent Hamiltonian does not close. That you can prove. So that's why we say these things define a phase, right? So you can, but the obstruction here is this: if this thing does not change, you can prove that there is a adiabatic path that connects these two.
But that condition does not sound like you can only by stating that you can construct explicitly. That's not just like a.
Well, you want the converse. You want that it's not in the same. That if it's not the same, that you cannot construct.
No, I mean to restrict to the major product state.
Yes.
If you if two states represent the same phase, if there's any compact mathematical characterization of this property instead of the state that they're connected by a dynamic gate.
I mean, yeah, I don't think I'm quite sure what you're asking about. I mean, I have an explicit construction for this path that interpolates between them. And that's all you need to satisfy that definition. I don't know if there's a more formal way of saying it.
I can ask you later.
Sure. Okay. Yes.
Since somebody mentioned higher form symmetries, can you classify SPTs using higher form symmetries?
Yes.
Is that equivalent to actually constructing that phi at the projective representation?
We will see in a bit. So I'm going to jump to, so there's no higher form symmetries in 1D, right? Or unless you think about points. We will talk about higher form symmetries in the next thing I wanted to talk about. We'll look at the higher dimensional version of this. There'll be higher form symmetries there. Well, actually, there's going to be both just global zero form symmetries, and then I can say something about one form symmetries there as well. But I think Carolyn is going to talk about higher form symmetries maybe in a bit more detail, so I didn't want to put it too much. Okay, let me jump to the higher dimensional version of this, and then we can. So this was for 1 plus 1D. Already you see that it's quite nice. You cannot do these kind of things quite explicitly. So in 2 plus 1D, in 2 plus 1, it's more interesting. Or because in 2 plus 1 you have something called intrinsic topological order. You don't need to impose symmetries in 2 plus 1 dimension to get interesting topological phases. Whereas in 1D, if I don't impose symmetry, as I mentioned, all injective MPSs are in the same phase. So in 2 plus 1D, there's an analog of this condition here. So, and it looks like this. So basically, you can have a tensor like this, x, g, e, like that. So the analog of this statement in 2 dimensions, well, basically of this thing, sorry, UG. So now I have a 2-dimensional state. I act on it with an on-site symmetry, and I say that the state is invariant. So this state is a symmetry of that state. The symmetry, it's a symmetry of that state. Then there's an if and only if, and then there's some asterisks. This has not been proven in full generality, but there are conditions of these tensors for which this is true. Then there exists this kind of, like this. There exists this virtual transformation here, this x of g, that I can push through this tensor that implements this group action, basically. So this u of g has some remnant on these versional degrees of freedom. Now, because I'm in 2D, this object, this transformation here, is not just a matrix anymore. It's something that has to act on these different, all these different legs. And this is what's called a matrix product operator. So above there, I defined here, a matrix product state. You can turn this into an operator by just adding additional legs here, right? So now this becomes an operator that acts on matrix product state. And that's what this thing here is. So this x of g, this is an MPO instead of an MPS. And now, if you look at the classification of how these things transform, so what you can again play the same game. So you can check if I look at the product of these two things, it forms a representation. So you can say, okay, I could look at the product of these two things and find again that there's an arbitrary phase in there. But that phase is not something that's stable under blocking. Just like the 1 cocycle is not something that's stable under blocking in 1 plus 1D. The 2 cocycle, which is telling you whether this is projective or not, is not stable under blocking in 2 plus 1 dimensions. So everything just shifts up by 1 dimension. So there's another invariant that you have to look at. And the way to define it is actually to look at the product of 3 of these guys. If you look at the product of x of g1, x of g2, x of g3, then there's 2 different ways of decomposing this locally. So you can either first do this, g12, g123, but you find that, okay, you can also do it the other way around. You can first do 2 and 3, g1, x1, g1, x, g2, x, g3. You can also do it the other way around. So first 2 and 3, and then 1 and 2. And you find that this has to be equal to each other up to a number that depends on g1, g2, and g3. That has to satisfy a 3 cocycle condition. So basically this omega is an element of h3 of g versus u1. So,
sorry, could I ask? Sorry, I should have asked earlier.
Yeah, sure.
What is on the upper left? What was that equality you wrote? I missed.
This one?
Yeah.
It's a 2D version of this equality here. So this is the equality that I derived from having a matrix product state that's invariant under the on-site action of a symmetry group.
Right.
This is the 2D version of that. So this is now for this 2D tensor network that I drew here.
Right.
I go through the same logic, and I end up with something that looks like this.
I think I understood that. So what is the right-hand side? You said that's equal to something.
This one? Oh, no, sorry. This is something that's called, we call this an MPO. So it's a matrix product operator.
Ah, that operator, but in the middle, just to the left of that.
This one?
Yeah.
Oh, this is just the right-hand side of this equation. This is this. Oh, okay, maybe yeah, no, that's exactly the same. Huh? Oh, maybe, okay, no, sorry.
So you have the matrix product state, and then
Sorry,
it
should be on this side, sorry. I don't know if that clears things up. So this is the physical leg here.
Right.
There's an action of this thing on the physical leg.
Ah, okay, I see.
This is a virtual thing.
Okay.
Here, this is the physical leg here, the one that's sticking out.
That's the UG, okay.
Yeah, sorry.
Okay, thank you.
And so it pushes through like that.
Sorry, Lawrence, this associativity diagram, can you just clarify what are these elements? Is it G1 times G2?
This is, yeah, sorry, this is G1 times G2. I'm just using it as a label here, really, G1, G2. So, this virtual index here, it depends on the specific G. So another way of labeling these operators is just by saying, I'm labeling this virtual line by just a notation. And then it's easy to label these tensors here that implement this local product. So these tensors are something that you can compute. Just from the fact that these have to form a representation, again using your fundamental theorem, actually you can deduce the existence of these kinds of tensors. And then you can look at this equation and you can derive that, okay, this equation has to be true up to this element here, which has to be a phase. And this phase, if you work it out a bit more, you find that this has to satisfy a triple-cycle condition, therefore it's classified by the third cohomology of G versus U. So actually, David, to answer your question, this is the anomaly here. This is what it means for a symmetry to be anomalous, or a finite group symmetry. If you have something like this, where this is non-trivial, so if you have a matrix product operator symmetry, where the local multiplication rules are only associative up to this phase here, that's something that's an obstruction to being able to make this thing on-site. It's an obstruction to being able to gauge these kind of symmetries. It's an obstruction to having a symmetric trivial gap ground state, so that's all sort of usual characterization of an anomalous symmetry.
Those are all things that usually happen in even space-time dimension, not odd space-time.
Yeah, sorry. So this is, I'm talking about virtual symmetries now of 2 plus 1D. You can use the symmetries, and this is what I will do maybe I think in the last lecture. You have to look at the boundary theory of these things, which then inherit this symmetry, and there it acts in an anomalous way. So this is an anomaly for a 1 plus 1D system, not a 2 plus 1D.
So suppose I have a system with a non-trivial omega.
Yeah.
Is this the Chern-Simons theorem?
Yes. Well, okay, Chern-Simons would be for like a continuous group, but okay, this is Chern-Simons at finite level, right? So like you can do that for cyclic groups.
To digraph Witten topology?
Yes. Yeah, exactly.
I mean, isn't this just an SPT?
Yeah, so this is SPT,
So
right?
you gauge that to get your digraph width.
Yes. So okay, what I didn't say is okay. So this is the SPT in 2 plus 1D.
You gauge G, basically.
Yeah. And then the statement that I wanted to make about anomalies in systems 1 plus 1D is about systems that live on the boundaries of non-trivial SPTs, which are 1 plus 1D theories in 2 plus 1D. So that's what it means to be.
Sorry, just maybe one more question for now.
Sure.
These, I think, just checking if I understood correctly, you're saying in either slide, okay, the phases of these matrix product states, G-invariant matrix product states, are classified by these cohomologies.
Yes.
Isn't it?
Yes.
Right, but then they also correspond to classification of certain topological field theories. That's what you were saying.
Yeah. So this is now the 2 plus 1D version, so you go up one level in cohomology.
And the same thing here as well. I guess there's some topological field theory.
Yeah, exactly. Yeah. So okay, these matrix product states. These are general, right? These represent states with arbitrary correlation lengths, generic points in the phase. However, if you look at renormalization group fixed point matrix product states, so matrix product states with correlation length 0, then there is a state sum construction for these kind of things that basically Degraaff-Witten or whatever. These kinds of constructions, they apply to these matrix product states, and they give you the exact RG fixed point matrix product states. But these matrix product states, they are used in a context that's much broader than just these RG fixed points. But indeed, there's a very strong connection, and we will use that connection actually to classify this. So yeah, I have 20 seconds left, but maybe I can get like, if I get like 2 more minutes, I can finish what I wanted to say. That sets me up nicely for the next lecture. So, in 2+1 dimensions, there's a slightly more interesting situation. Okay, I mentioned that it's more interesting. What do I mean by that? In 2+1D, we know that we have something called intrinsic topological order, which is something that appears already if you're not imposing a group symmetry. And the way to understand that is that if you look at the theory of these tensor networks, what you find is that actually in 2+1D, you can actually find non-trivial solutions of this equation on the top there without a UG, or let's say that the UG acts trivially. So you don't need UG, OA. You don't need this U of G to get interesting solutions to just this equation. In 1D this is not possible. If in 1D, if you don't have this property here, if you don't have this UG, then this is saying there is something that commutes with A, but I mentioned that A spans the full matrix algebra, so that's a contradiction. The only thing that commutes with something that generates the full matrix algebra is the identity. Here, it's a bit more subtle, and I'm not going to go into the technical details, but basically here you don't have that restriction, so here you find that already for just these tensors, there are these non-virtual, these non-trivial matrix product operators that you can pull through. But now, because these don't have to correspond to a physical action anymore, there's actually no reason that these operators have to be invertible. Right? These don't have to be representations of a group anymore. These can be something more general. And that something more general sort of becomes obvious if you write the equivalent of this condition in this language. So what you find is that OA, OB, OC times do the same thing. So you look at 2 ways of reducing this. So this fuses to E, this fuses to D. This is going to be some sum over F of F, A, B, C, D, E, F of the same picture, but then OA, OB, OC. F, E. Right. So if I look at the ways these things have to fuse, okay, you will find that the only thing that's consistent is that these things are representations of a fusion ring. And then if you look at the local associativity of this product, you will find that there's a number that pops out here. This number, if you do this for 4 of these guys, you will find it has to satisfy a pentagon equation. So this thing defines a fusion category. This matrix product operator, you can think of it as being the representation of some fusion category symmetry. And so you find that in 2+1D, contrary to 1+1D, there are tensors without imposing any physical symmetries that have these non-trivial virtual symmetries. These virtual symmetries are described by fusion categories, and these are going to be what give you topological order. So it's known that topological orders in 2+1 dimensions are classified by fusion categories, and this is kind of a tensor network derivation of that statement. Now, it's important to stress that this is general, right? So I'm not just imposing this for RG fixed point tensors. These are not just tensors that are coming from some TQFT state sum construction. No, these are general tensors with some arbitrary correlation length in some given phase. And they satisfy this property. So this is a way of talking about these phases in a way away from the RG fixed point as well. Now, having said that, what I want to do in next lecture, to kind of get some intuition about these kind of things, is I want to talk about exact solutions of these things constructed from TQFT. So basically, I'm going to use something like a state sum construction to construct exact solutions of these things. I think that's something that maybe Niels will also talk about a little bit, about state sums, but you will see that we talk about it in a very different way. Okay, so with that, that's sort of everything I wanted to say for this lecture. Yes?
Question. Which characteristic of perhaps tells you that you have interacting Hamiltonian?
You mean
So I guess all these things can appear only if you have an interacting Hamiltonian, right?
By which you mean what? It's not commuting projector, or what do you mean?
Yeah, I mean, is this the dimensionality of the Hilbert space or something that tells you that your Hamiltonian is interacting? We don't expect these properties to emerge in free Hamiltonians.
Oh, no. Well, if you just have some on-site Hamiltonian, that's not...
It's not about free fermions.
Oh, free fermions. I see.
So this wouldn't appear for free fermions.
No.
What characteristic of your PEPs tells you that you have?
Well, for free fermions, all these PEPs are Gaussian, right? Ground states of free fermion PEPs of free fermion Hamiltonians are Gaussian PEPs. They are PEPs with very specific properties that don't have these kind of things. I think, okay, you're probably talking about like the classification of topological insulators and all these kinds of things. That's what you're thinking about, or?
I mean, these properties should emerge only if you have an interacting Hamiltonian.
Sure, yeah. So for sure, all these. So an example of this will be, well, not the toric code, but that's not a. Toric code is not a free fermion theory, right? So indeed, you need interacting theory.
Right. Actually, so what ingredient in your PEP description tells me that I have interactions in my system?
So you mean just given some generic PEPs, how do I tell that it's the ground state of an interacting Hamiltonian? Or?
That's right, yeah.
Yeah, I'm not quite sure how you would. I don't know, Frank, if you have a...
It doesn't make any distinction between interacting and not.
Yeah.
So some are interacting, some are not, but the symmetries are the same.
But you cannot, okay, I think the question is more, you cannot get these non-trivial kind of things. I mean, you cannot get a fusion category topological order from some non-interacting theory. That's clear, right? I mean, already toric code is an interacting theory.
There's a very nice example in 1D. In 1D, classification of SPT phases is different for free fermions than for interacting phases. And with the NPS, you get the classification of time reversal invariant SPT phases. For fermions, you get a Z8 in terms of NPS, but you get Z if you impose that it's a free system.
So it's a type of symmetry, or
so you get
something.
So indeed, if you don't impose that it's free fermions, you have more paths to explore, and that's why the classification of Z collapses to Z8.
But that's for 1D, right? Yeah, that's 1D.
Okay, so we're going to have a break now outside, and we can continue asking more questions later. Maybe let's thank him again.